We'll go ahead and jump into this session for Monday. This is our basically our tech skills engine platform of the week. We try to go over this at least one every Monday and kind of give you guys a little rundown of basically the platform, the failures, the fixes, things that we do different to address those issues that plague that particular platform. And for those that were not able to join, we've recorded this session so that you guys might be able to look at it later, refer back to it, watch it at your convenience. This is primarily designed for the people of sales departments and different things for our WDs and our dealer network. But we're using these videos and putting them up on YouTube so that you guys can check this content out. Now, keep in mind it is recorded, but although it's recorded, we do check our comments in the YouTube platform. So if you've got some questions about this, whether you're a WD, you're a dealer, or you're just a truck owner, an enthusiast that might have some questions, always encourage that because that makes it really easy for me for the next time to have with having those questions. It makes a lot more interesting content. Sometimes it's questions that I hadn't thought about covering before, and that's really helpful for us. So today we're going to be covering, we've covered the 6.7 Powerstroke platform in our previous video. I guess this was about 3 weeks ago. We also covered the 6.4 liter. You can guess today which direction we're headed. We kind of started from the newest engine, and now we're working our way down to the oldest engine, which looks like next week's is probably going to be the 7.3 liter. So that gives us the whole coverage of all of the Powerstroke platforms. After we've covered this last one next week, we'll start in on the Cummins ISB series Cummins engines and kind of go over some of the failures and the fixes on those engines. Once we've gone through the 6.7 liter, we try to go through specific, not just an ISB series, but something that is particular to that very platform, that particular part number. We might address the 6.7. However, we'll probably split that up as we go, and we'll start addressing maybe the 2019s and up, maybe the 2018s down to 07.5, and then the 5.9s. We'll split those up from common rail, storm, and 12 valve, so that we get a really deep dive into each topic, into each platform. So it's it's necessary to do so because just because it's a Ford engine or a Cummins or a Powerstroke or a Duramax or whatever, there's a lot more things that are prone to certain year models, certain makes. It's interesting to note that just 1 year apart sometimes can make a major difference because of castings, because of parts used, processes, whatever it might be. But they change, and because of that, it really necessitates our look into that particular platform and that particular year model. So today we're going to actually bunch this together. I'll split it up. It's not so much that it's not needful to have a multiple webinars for the 6.0. We can group all the problems that they've got into one lump sum, the 2003 to 2007 in the F series. For you sales guys that don't know, that engine was actually used all the way to 2010 in the E series. Keep in mind that all your international engines and all your Ford engines pretty much run neck and neck with, they have their, I guess we could call it their alternate personality, right? They've got the Dr. Jekyll and Mr. Hyde. They've got the 6.0 Ford Powerstroke, but they've also coined it the VT365, which is what the international version is. If you go backwards to the 7.3 liter Powerstroke, it also can be the 444E, which stands for electronic version of the 7.3 liter. It's the same engine, the 94.5 all the way to the 03. It's still the same 444. It's 444 cubic inch displacement with the VT365. It's just the displacement. Same thing with the 6.4 Powerstroke. The 6.4 Powerstroke is also known as the Max Force 7. So while there are quite a bit of differences, in certain Max Force 7 engines that they are not actually interchangeable. There are some that actually are interchangeable. Now, when I say interchangeable, I'm using that term very loosely because emission standards on certain platforms are necessary to use certain combustion bowls in order to achieve that. But will the parts, geometrically speaking, fit into that platform? Yes, they will. So we can use a Max Force 7 piston in a 6.4 liter application if we chose to do so. That being said, going back, the VT365 is also known for the guys in the industrial, and I'm going to probably start doing more of the cover more a little bit of the industrial application as I'm going through this stuff, which is not necessarily, somebody may not think about this. That's a truck sales depot or something like that for the Ford pickup. But obviously our platforms cover a lot more areas than a lot of times than just what was used as the F-Series pickup. Now, Ford, as far as we're concerned, they weren't in the industrial application of this particular engine. However, International was the one that designed and made this engine for them. And because of that, International is a over-the-road and industrial application engine manufacturer. So they're not going to just build one engine for one particular platform. They're actually going to use it in a couple of different ways. You'll see this in the low cab Ford engines, or excuse me, the low cab Ford, over the cab Ford truck platforms as well, which is actually known as a VT275. It's the exact same it's the exact same engine. I shouldn't say exact. It's very similar. It's like its little brother. It's 2 cylinders less, so it's actually a V6 engine. It does use a dual sequential turbocharger setup, which was interesting because the 6.4 liter is not actually the first one to do that. It was a VT275. You don't see a lot of those out there. They didn't have a very good tenure. They didn't last very long. They weren't used for a lot of stuff, but they were used for the LCF trucks. So if you ever get a phone call for the VT275, just know we do manufacture those as well. It's just the same, like I said, as far as long blocks are concerned, whack off 2 cylinders and there you go. But anyways, without further ado, let's go ahead and kind of get into some of the things that were going on with Ford. Obviously, 2003 had came to pass, and the EPA was knocking at the door again of these manufacturers. Cummins, we started seeing doing quite a bit of changing. From 91.5 was really the first year of the EPA actually came out, and for the trucks that they were really, for the diesel market, cracking down and saying, okay, we need to do something a little bit different. A lot of guys really don't know that. I mean, for us, the major changes really came about when we started seeing differences in EGR recirculation systems and diesel particulate filters, selective catalyst reduction systems, and things like that. But 91.5 was actually the first year in the pickup truck that they started saying, okay, for the diesel guys, this is what we need you to do. So they did that again in 98.5. But the deal with it is Ford did do a design change as well. In the F-Series pickup truck, you'll note that there was no true 98 model pickup. They went straight from 97 with the OBS, the old body style, to the 99. And the 99 would be the F-Series, the Super Duty is what we know it as. And there was a difference in the engine itself and the 7.3s, and we'll get into that next week when we start looking at the single shot versus the split shot injectors. But the thing that you really want to note is they had this change that came up about 2003. Actually, it was 04.5 is actually when the EPA, they were ahead of their curve on this. But 04.5 was when the EPA mandate actually came for the tier. Let me see, that was a tier 3, I believe, emissions change on that. Don't hold me to that. I could be wrong on it. But at any rate, with that being said, Ford was already ready to make the change. They'd had a great successful run with the 7.3 liter. It was just the workhorse of their lineup. They really had been very successful. They sold a lot of trucks. They had a huge following. The Ford Powerstroke engine was a game changer for them because they did not have anything really to compete with Cummins before the days of the direct injection. They didn't start turbocharging those engines till about 93 was when they first started coming on the scene. At any rate, the 2003 was a big deal because it was a split year. They kept that 7.3, and then they made the change. And when they made the change, they introduced, behold, the 6.0 Powerstroke diesel engine, which has been heralded as the most problematic diesel that Ford has ever put their name on. But then the 6.4 liter said, here, the proverbial kind of hold my beer thing. Well, the 6.4 liter said, step out of the way. We can do better. And they were much more problematic than the 6 liter. And there was reasons why they were much more problematic than the 6 liter. That being said, we kind of covered a lot of those things with the last webinar that we did about 2 weeks ago. But this being said, going back, the 6 liter 2003, new emissions, new changes. There was a lot of things that had not happened before. Obviously, until 2003 came out with a 6 liter, we hadn't seen the EGR in the 48 states, anyways. We hadn't seen that placed on an engine. The EGR system alone is what led to the detriment, what led to the decline, what led to the disaster that Ford Motor Company experienced with the 6 liter. Now, this began a huge problem with the relationship between Ford and International, which would turn out to be a long, bloody battle between them in court and ultimately lead to their separation. But the 6 liter, the EGR was what killed that engine. If you had to identify one single component that actually killed it, for sure, hands down, it was the EGR. So I guess without further ado, we'll go ahead and just start there. That's about as good a place as any. So what we see in that with that engine failure, it's kind of like I always think of that song, "The knee bone's connected to the shin bone" kind of thing, and this is just a domino effect of problems. So we start seeing something that, let me see if I can pull up this picture for you, if I can get my mouse working right, that becomes very, very problematic. Let's see. I've got a photo right here, and there we go. All right, so there we go. Yeah. So this is a picture of an oil cooler. Many of you, if you've ever worked on 6 liters, I can promise you that you've replaced an oil cooler at some point in time. This oil cooler has a lot of silicate and sediment in it, and that's from the casting of the block. The thing that Ford does differently than does GM in the Duramax, as does Cummins in their platform, is the oil cooler design is a sandwich oil cooler design. So you've basically got 7 layers of coolant, 7 layers of oil, and you have coolant, oil, coolant, oil, coolant, oil all the way through. The problem with it is that oil cooler was also what was necessary. It passes, so the coolant basically comes out of the front cover, and it goes into the oil cooler. As it goes through the oil cooler, it goes back through the EGR cooler. If the oil cooler gets stopped up like this does, there are heat exchanger tubes that are inside of this EGR cooler. And let me see if I can back this up. See if I get, I don't know if we got a good picture of that. I was trying to put together some pictures for you guys beforehand. You can see this nasty gunk that's going on inside. This is actually the EGR cooler here. This is the EGR valve the guy's holding in his hand. And you can see that the line coming out of it, going back into the intake manifold. So the problem with it is the heat exchanger tubes. It's just like anything else. When you expand, when metal gets, when it heats up past basically the integrity of the material, it expands and contracts and expands and contracts. But it'll eventually weaken that material. And you can just very, very faintly see up at the top the tube that we're talking about. But what happens is eventually it will wind up cracking. Now, this is quite different than the 6.7 liter. They learned a lot because they were trying to put this on the cold side. The EGR was getting gummed up already without the problems that they already had. And they learned that by running the EGR cooler on the cold side of things instead of the exhaust side, it was leading to a lot more sticking of the EGR valve. your P0401, P0404, P0403. All those codes were present for the EGR cooler. Now, what would happen, and there were ways to diagnose this to see if you had a valve sticking open. Obviously, if your valve's sticking open, your engine performance is going to be greatly reduced because of the density of the air that's going into the intake. So what would happen is this gunk that you're seeing was a culmination of soot and coolant. So now you have an engine that's shutting off. When you shut down, you turn the engine off and you go inside, you come back out. The coolant system stays pressurized until it cools to ambient temperature. And that pressure is going to remain in the system. The problem with it is that pressure that remains in the system is always going to work from a high pressure down to a low pressure. It's going to move in the path of least resistance. When that takes place, it pushes into the cooler here. It's pushing all the way into the intake. Now we have coolant sitting on top of the piston or into the intake manifold. And as soon as you start the engine up, the low pressure area again in the cylinder is going to move that direction. And now we're trying to compress a liquid, which does not work out really well. It leads to another failure, which we'll mention here in just a second. So I'll pull this thing up. So we've got the EGR cooler that's failed, and moving on, we're going to wind up showing you, I've got a picture right here that everybody that's ever dealt with the 6-liter is very, very familiar with this particular problem. Let me move this back over. Give me 1 second. Yep, there we go. Anybody that's ever worked on a 6-liter is very familiar with this common problem, and it's blown head gaskets. So you've got a non-compressible that you're trying to compress, and what happens is that now it cannot compress this coolant that's sitting on top of the piston. Something's got to give. A buddy of mine, we talk about this all the time. Chuck Lynch from ARA is always talking about fuses, and you see the guy that's always burning out. It looks like the guy on A Christmas Story, that he's popping fuses because he's got one too many, in his outlet. And what they do is they tend to grab a larger fuse. And then when the fire truck comes up and the fire department comes out and the insurance company comes out to find out why the man's house burned down, they found out that he put a 100 amp fuse in place of a 15 amp, but he fixed the problem, right? Well, no, he didn't. He moved it down to another place. Now he's actually looking for a new place to live because he burnt the house down. Well, this is the same thing. We wind up having this non-compressible, and something's got to give. The fuse is the actual, not really the head gasket was never the problem. Now, keep in mind, there was one big thing that they did change, which a lot of folks pointed fingers at, and I'll agree that obviously our clamping force was greatly reduced because they changed on this cylinder head. We've got 20 bolts, you've got 4 bolts per cylinder head. So what you're looking at is a big problem because we don't have the same clamping force from a mechanism to hold that cylinder head down. The problem with it is not actually the head gasket, nor is it the clamping force. Totally, the finger to be pointed at really and truly needs to be back with the silicate and with the contaminants and the sediment that was in the block that blocked in the poor design of the oil cooler, which led to the EGR cooler failure, which led to the head bolt failure. So what we start running into is the elongation of the head bolts. So basically what that looks like, and I've got a picture of that somewhere here. Let's see if I can pull this up for you guys. So this is now obviously it's not a head bolt, so it looks like a rod bolt. But you can see the necking is basically the elongation that's taking place of the of this bolt, and that's essentially what's happened to the torque yield bolt. As the piston's coming up, it's pushing that coolant up against the head, and something's got to give, and the bolts do. And so now we have blown head gaskets. And that turns into a whole big issue where a couple $1 million a month was being spent by Ford Motor Company for warranty claims. And so we see a tremendous amount of problems with the head gasket failures. Now, that we determined what the cause for that was. Now, let me say this. That is not the only cause for head gasket failures. What people do not realize is that the biggest cause for head gasket failure after the EGR cooler, the runner-up, is this exhaust back pressure sensor. If I owned a 6-liter I don't care if it was studded or not. There's something that I would probably do once a month, and that was to make sure that I checked my exhaust back pressure sensor against my barometric pressure. The bad thing about these things are, and this is, I've shared this with a 6.4 liter, but the bad thing about these things are is that if this exhaust back pressure sensor gets plugged, it is what the ECM looks at to determine the vane position of the turbocharger. So if we have a plugged EGR, plugged exhaust back pressure sensor, it starts commanding a tremendous amount more boost pressure through means of the geometry of the variable nozzle turbo or the variable geometry turbo. Take your pick. But anyways, it starts coning it down, and it's almost like taking a sheet of paper. And the way it works, to give you a quick 5-second explanation of this, is basically if you were to take the velocity of air that was moving through a larger area, and if we cone it down, obviously, and we take this and we twist it down, but we do not change the volume that's running through that piece of paper, we're going to increase the velocity that's running through it. Now, that's the mindset, or that's the idea, the engineering behind the VGT turbo. The problem with it is the coning down of that takes place in order to achieve the desired boost pressure is going to cause what we call drive pressures. Drive pressures are basically what, if a boost pressure is the positive pressure that's placed on the intake side, the drive pressure is the amount of pressure on the exhaust side. And again, we're trying to, this is for really for the salespeople that are trying to understand maybe some of the terminology that you might encounter when people start talking about what your drive pressures are. Your drive pressure is basically the pressure that's coming out, and it's derived by the cylinders and what's exiting the cylinders. So if we have high drive pressures, we can basically determine that at some point in time we've got some type of proverbial potato in the tailpipe, so to speak. Well, the VGT, and I think I've got a picture of that for you up here. This is a turbocharger that's actually broken down with the exhaust off of it. This is called the VGT, or the variable geometry turbo, and the vanes that you see inside that turbo move based off of a unison ring. And I don't know if you can see my cursor or not, but you can actually see these little oval type shapes on top of these vanes, and there's a unison ring that runs on top, and it's centered off of this pin that's sitting right here on top of the turbocharger. What happens is that now you've compounded the problem, because we've got an exhaust back pressure sensor that gets plugged. That's one thing. Now, you placed it in the worst possible area. You put it inside the exhaust. Well, we know that hydrocarbons have to burn off around 740 degrees. So soot is something that's very well known with the diesel community. It's something that's going to accumulate just like any other internal combustion engine. But now we placed a sensor that's in line with that. When it becomes clogged, now what happens is these vanes that you're looking at are going to cone down to increase the velocity, because it's actually not registering on your ECM. If you looked at your ECM and you have a sensor that's completely stopped up, the ECM's not even showing that this thing's actually making any boost pressure. Yet you may be building 20 pounds of boost, but it can't read it because it's stopped up. So it continues to ask for more boost pressure and more boost pressure and more boost pressure, and it continues to cone down, as I call it, the vanes that are in the turbo. When this happens, you notice this noise when you let off the accelerator of the shoo, 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 shoo. And it's kind of like a turbo bark, they call it. Basically, what's happening is that it's trying to push the air now. You've increased the amount of pressure inside of the intake, and you let off. That air can go nowhere. So it tries to take the turbocharger and spin it back the other direction. And when this thing takes place, that's where you're hearing that noise come from. That's a quick way to know that something's going on with the EVP most times. So that's a key thing when you're talking to a customer that's installing a new engine. The way that we check that, and for our preferred dealers, we add a whole checklist with this, and we ask for this to be recorded. What we want you to do is we want you to take the key to the run position. We want to take a measurement of, with the plugged in, obviously, the exhaust back pressure, which should be close to within a pound or two, no more, of barometric pressure. So we should be able to look and see the difference between what your barometric pressure is based off of whatever that day might be, whatever your whatever that may, most of the time it's barometric pressure is going to be 1 bar, 14 pound, 14.7, but it's going to depend on elevation and barometric pressure that's going to give you that reading. We want to see that within a couple pounds. So you look at that, you look at your EBP, and that should tell you whether or not you're having issues there. Now, if you let the truck sit long enough, obviously, you come back and you turn the key to the run position, it is a chance that you are going to see the same pressure based off your barometric pressure, because everything is basically neutral at that point. So we encourage you to start the truck up. You can brake torque it for a couple seconds. Doesn't even take that long. If we don't see any increase in the exhaust back pressure, and there's a huge difference between your drive pressure and your boost pressure, then we need to take a look at that sensor and get that taken care of, because that will lead with the excessive boost pressures. That will cause a head to lift, and that'll cause blown head gaskets. And you can have that problem again and again and again. And it's the fix is not to put the bigger fuse in it. It is actually to wire the house with the right wiring, or reduce the load, or do whatever it needs to be to actually fix that problem. So looking at this now, one of the other things that we can see is you've got some contamination, some rust and pitting and different things like that. When coolant goes through your exhaust, there's a couple of things that take place. Coolant is extremely corrosive to cylinder walls, to bearings, to metal material. That's a whole nother ball of wax that we could talk about. Just how bad it cavitates bearings and cavitates cylinder walls. I've seen brand new engines that were, well, I'll say brand new, 60,000 mile engines that would have these kind of failures. And when you would pull a head gasket off, typically what happens is the guy has a head gasket failure and then turns the key off and then just waits for the mechanic to fix it, or he drives it up there or tows it up there or whatever. And that engine might be sitting for weeks before they actually get the head off. When you do get the head off, what you notice is wherever that piston stopped and the coolant set, there's now tremendous amounts of cavitation that occurred in the cylinder wall. And it's just heartbreaking when you look at that, because you go, I could have fixed this really, really inexpensively, but now we've got to deal with an entire engine issue. That's one thing that's really detrimental. The other part of it is that all the coolant and all the trash that goes through the turbocharger can cause the vanes to eventually stick. And when those vanes stick, the same effect takes place. Now you run into issues with some of the, my memory just now escapes me, but some of the different turbocharger codes that you wind up getting for non-vane actuation. And it doesn't matter what your solenoid is trying to do, it cannot physically move these. So what you'll see is a loss of boost pressure, or you'll also, it depends on where they stick, you can run into problems with that, either not building boost or building too much boost. Trying to see where we actually want to look at the next problem. While we're on the oil cooler subject, let me pull this up. This is probably the most expensive failure point of the 6-liter engine. Now, this is a standpipe that we took out of a vehicle. Well, this was a standpipe that we took out a vehicle. The filter would go over where the spring area is, where the guy's hand is. I think that's my hand. Yeah, I think that is. It is my hand. But anyways, the filter should have gone over. It's melted. What happens is when it melts, that composite, that material, winds up migrating and finding its way through every orifice, and it's headed to one direction. And that direction is it's trying to get down to the crankshaft, because that's where the oil is routed, right? Typically, that's where we wind up seeing this stuff make it, and it winds up wiping out a bearing. How does all this come about? Obviously, oil temperatures are extremely important on a 6-liter. They're important on every engine. But why the 6-liter tends to have more issues with oil temperatures running higher than everybody else's is pretty easy to figure out when you consider, I say this all the time, what HUE injection stands for most of the world is hydraulically actuated, electronically controlled unit injectors. For us, it stands for helping engines against uneducated installers. And that's because you can run this thing out of oil and it's going to shut off before it gets out of oil. That's the beauty of the 6-liter. It has a built-in fail-proof, idiot-proof engine. For the most part. Now, the issue is that oil does tend to get hotter. The reason why is because you're using an oil now as a hydraulic to compress the intensifier piston in the injector, which is basically a multiplier of 7. So we'll get to that in just a second. But anyways, that being said, the oil gets really hot because of the combined gas law. For any given, and I've said this in other podcasts, but basically the way it works is when you compress something, it has basically a ratio of what you're compressing to what the temperature, your pressure and your temperature, or a PT chart. We see that on like 134A is a really good example because it's a 1-to-1 ratio. So I've said before, you guys that are running, looking at your air conditioner on 134 and it gets down to about 33 pounds, at that point in time, we start seeing it freeze up because 32 degrees is freezing. So your pressure to temperature is going to run 1-to-1, pretty close to it on 134. Same thing with this. The more pressure that we put into this, the more heat that we're putting into this, we're seeing about 3,600 pounds of oil pressure, just depending on what the application of the engine is. If this oil cooler gets stopped up and it cannot provide the necessary means to dissipate the heat that is so imperative for this engine to make a long, happy life, and all engines for that case, it is important that we note that early on before things go bad, because there's a lot of things, not just spun main bearings, that can go bad from here. Generally what you'll see is guys complaining of, man, I've replaced my standpipes. I can't tell you, I've got a bad batch of standpipes. I got a bad batch of injector O-rings. I've got a bad batch of O-rings that go in the injector, the nipples, that they're just, seems like, man, I just got high pressure oil leaks coming out wazoo and I can't get this thing to stop. Well, reason why is many times that oil temperatures will cause that, and it'll cause erosion. It'll cause premature failure of the O-rings in the HUE system, because as this oil begins to break down, as it gets hotter, so do the O-rings. Now, that's not the only thing that will kill your high oil temperatures is not the only thing that will actually kill that engine. Let me see if I can find, here we go. So this is something that's we actually we have a Diesel Masters video. If you guys are watching this, I'm always shocked at how many guys actually are still interested in 6-liter stuff. It seems like if we're not on the cusp of what's going on, like the newest, the latest, greatest, I always feel like I'm backing up. But there's so many guys out there still running these 6-liters. It's really, really interesting, this stuff. And we tend to have more, funny enough, we tend to have more views off of a 6-liter than we do any other engine. I don't know exactly why that is, but we have a Diesel Masters YouTube on our channel as well. We go through a 6.4 liter, and I think this is where this photo came off of, if I'm not mistaken. You can see on this photo the small needle bearings that are actually impregnated into the gear-rotor style pump. And so through the gear-rotor style pump, you have 2 gears that are basically running with a specified clearance, and there's very little clearance between these 2 gears. And the only thing that's allowing any trash into this pump is obviously, as it goes through the filter, on the pickup screen, there's a mesh down there on the that's welded to the pickup tube. The only material, apparatus, whatever, that's small enough to fit through that particular mesh is actually the needle bearing. So when you pull this out, it's always the needle bearing that fails, if that's what you're seeing. And it leaves a nice impregnation marking there for you. So what's happened is that the oil pump didn't just fail, trash didn't just get in it. The oil temperatures failed, or they became extremely hot, and your lifter is your fastest running bearing in the whole engine, and this is what you end up with. You start having breakdown of the needle bearings on the lifter, and inside right here on the axle, the needle bearings are what supports that. And once they depart the chat, they enter into the oil pump, and then that causes the oil pump to fail and the truck to shut off. Before that, you might hear guys saying, man, I just heard a chirping sound. I don't know, it sounded like a turkey call or something. I don't really know what's going on with my truck. And they'll continue to run it. And when they do, actually, I got a video right before I jumped on this thing. I was looking for some pictures, and I noticed on that on that video, I went through a customer's complaint. He had a question. He called in or texted, I forget, but whatever. And that was one of the things he said. It's like, man, I heard it sound like a chirping noise or something right before everything went south. If you're an ounce of prevention is worth a pound of cure. And if you will listen to what's going on, you can certainly save yourself a whole lot of money. Now, this being said, while we're in the oil pump vicinity, we want to talk a little bit about balancing. And you go, what does balancing got to do with oil pumps? Well, it's got everything to do with oil pumps. I'm sorry, Christy, I appreciate the scan me thing, but I am not smart enough. Well, maybe I can figure out how to get that on there. So what does oil pump have to do with balancing? So there are guys out there, and I'm certainly not the enemy or the adversary for a billet oil pump. But there again, we need to understand what's causing the failure. People love to make billet parts. I've often said people would buy billet seat covers if you could make them, even though that they weren't comfortable, they look pretty. But there's always something in the aftermarket world that somebody's willing to sell you. And I'm not saying that it's a bad idea. I'm saying that you need to address the concern. You need to address the root of the problem. Don't go slapping another fuse in this thing. So what we typically see is that you see the crack that happened. Obviously, there's multiple cracks in this thing. I think I've got my screen. I don't know if I do or not. Yeah. Okay. You see the crack in the housing. You see the crack in the inner pump gear, and you see the crack actually on the outer. Now, there's a reason for it. What typically happens, and these are the reasons why we see these failures. That guy's running a lot of RPM. He's generally running a lot of aftermarket power adders, we can call it. So what happens is the guy cracks his gears, he cracks his front cover, and the next thing he knows is he's online and he's seeing some video where somebody put in some billet front cover gears. Well, that's great. There's a reason why this fails, and I'll explain it. When you begin to increase RPM past what the engine is typically designed to run, when you start adding a lot more power, you're putting a lot more duress into the crankshaft. The order of imbalance that takes place is a lot greater. Now, the harmonic balancer, acting as a shock absorber, has to be able to settle the crankshaft back down each time this event of a detonation occurs. And so there is different types of balancers, but the factory balancer cannot maintain the load that's being placed on the crankshaft. It cannot. What winds up happening is that basically the rubber ring that's inside of the balancer will begin to separate from the material that is bonded to, and that's one part of it. The other part of it is these crankshafts, as we have done some testing on things, we found typically around 35 to 40 grams of imbalance is generally what happens. The snout of that crankshaft begins to orbit, and it doesn't settle. It begins to orbit, and when it begins to orbit, what's attached to the crankshaft is obviously the gears. They're trying to run as concentrically as they possibly can. The issue is that there's very little clearance, and as the snout goes into orbit, the gears go into orbit, but they're constrained by the front cover. So not only are you running into issues with you're causing basically a cavitation issue of the oil, because each time those clearances are taken up, because the crankshaft is now moving on you, you're starving the engine out. It becomes a erratic supply of oil. It's not consistent, but it continues to go. And then now we've got this gear that's pushing up against the housing of the front cover, and you start seeing that's where you're seeing some of the cracking that's going on there. But there's binding up of the gears. Once the two gears crack, it's kind of what came first, the chicken or the egg, because once the inner gear breaks, it's going to now bind as it's trying to go around. Well, when that happens, then it's going to wind up pushing outward in the front cover, and it's going to cause that to prematurely fail. The problem with it is that we have noticed, and I've personally done some testing on this, if I can take and balance the engine down to greater or higher standards, let's just say that, I can get this under control, and I don't have that failure anymore. I've got some trucks out there that we've tested on, and we spun at a lot higher RPM, 5,200 RPM, 5,300 RPM, and still are able to keep that crankshaft in in control without the whipping of that snout that takes place. I'm not saying that a billet set of gears isn't a nice little add-on, but I'm telling you right now, that's not the reason for the failure. The reason for the failure is trying to control the snout of that crankshaft through imbalance and through excessive forces that are being applied to a harmonic balancer that is not designed for that. Moving on, we've kind of covered that. We were still on the subject of the lifters. Now, this is one thing that's quite different. For the 6.0 and the 6.4, they use different push rods. They used a 9-inch 849 thousandths push rod on the 6-liter, whereas they went to a 9-inch 800 on the 6.4. Now, there's about 108 thousandths preload on that lifter. If you bottom the lifter out, again, it acts as basically like a hydraulic shock absorber as well for the valve train. But when you bottom it out, now it becomes very, very rigid. So each impact that it takes, it's taking and it's transferring that into the internal components of the lifter, and that causes premature failure. So correct preload for the lifter is absolutely imperative. And that's the reason why they decided to change, because of some of the premature failures they were seeing on the lifters. So that being said, it's always a good idea. We encourage if you're overhauling this engine or whatever, it's always a great idea to change to a different push rod that's a little bit shorter, the 6.4 style. Keep in mind the 6.4 still uses the same exact same exact lifter. The deck height of the blocks is the same, and so it was an issue that Ford found. I wouldn't say early on; they were about 4 years into this thing before they changed it. That being said, that pretty much concludes the lifter failure portion of this. But going on where we're at the cylinder head side, there was a notorious failure there, and we can kind of cover some of that as well. This is a cross-sectional done by Accurate Diesel, and it really tends to help the here we go. There we go. That's better. The explanation of this. You can look at this and see there's basically two injectors on a 6-liter injector. The bottom, if I remember right, one's black and one's white, and it's separating the fuel from the oil. Now, it's encapsulating that fuel. Where you see the fuel galley is where it's basically cross-drilled into the injector bore. Now, what happens is that your injector hold down. Now, this picture doesn't actually show it, but just where the hand is, I don't know if you can see it right above the green coolant passage, just as it would be coming towards us, the injector hold down is right over that area. And what happens is these guys, and it's not necessarily a fault of the person that's doing the installation, it is a weak point in that casting, but it is exacerbated by installation errors sometimes. Obviously, like I say, it is a weak point in the casting, so I'm not blaming anybody that's doing the installation, but it's something to be cognizant of. And here's the reason why. You can take your truck or you can take your cylinder head to a machine shop, and they can do the machine work for it and everything else, and they can pressure test it for you, and they can give it back to you and said everything was just right. We've checked it out, everything's good. And they may know very well the problems of that cylinder head, and because they know it, they're going to check it. They give it back to you, say everything's a-okay, you're ready to go. And you get over there and you torque the injector, and you over torque the injector, because a lot of people don't use torque wrenches, unfortunately, and they pull on the boss area of that injector hold down, and it winds up cracking right above the injector cup. And now you've got an issue, because coolant and fuel are now sharing the same cavity, but one has more pressure than the other. And the one that has more pressure is the fuel. It runs at around 45 to 55 PSI, depending on if you got a blue spring kit in it or something like that. But it overpowers and overcomes and overwhelms the coolant passage. So now it's pushing fuel into the coolant. And now next thing you know is you've got another fluid that's floating on top because oil and water don't mix. You've got the coolant and the fuel now, because it's petroleum based. It's floating on top of the of your coolant, and the problem with that is that fuel is extremely corrosive, again, to the seals inside of the radiator, the water pump, and heater core. So you really, really, really don't want that stuff staying in there. Eventually it'll grow to the point, depending on how bad the leak is, but typically, you kind of have to, I've seen guys take and try to bleed these things off until they can get it fixed. The issue is if you don't get it resolved quickly, then what you'll wind up having to do is replace a lot more components of the coolant system than what you want to. Typically what I see is a lot of the water pumps fail after this type of failure shortly thereafter. So the fix for this, obviously we have aftermarket castings made for us that really help, because they are thicker in that one area without being too much thicker in any other area that would be detrimental to the cooling system. But it's reinforced. The other thing is there is and I will say this because we're using their picture, they have a cup that extends above that fuel galley, so that it actually extends up past the crack. And there is I'm not sure what type of what model Loctite they use, but it seals that crack to itself, so it doesn't have that issue. And that's depending on what you're doing, that may be a viable fix for you. Cylinder heads, there we go. I think I stole this one from Engine Builder, or Engine Professional magazine here. So I want to give them kudos. Definitely check those guys out. Valve recession is something that's imperative. It's really important. And the thing about valve recession is, and these are the things to know, when you're buying from Choate Engineering Performance, we're very cognizant of the valve train geometry and the effects that it has. And I've said this once, and if I've said it once, I've said it 1,000 times. But an engine is not something that you can change one thing and it's an isolated event. It is a domino effect of things that happen. And there's a lot of things going on by changing valve recessions. Now, valve recessions, for those that are not gearheads, I understand like I said, we're talking to a lot of sales personnel that might not know anything about that. Basically, if you can see where my little hand is above that valve, it would be the dimension from the top of the face to the top of the head, right above here. And that call out typically was like 13 to 27 thousandths initially, which was too shallow, in my opinion. And so that valve recession, what winds up happening is sometimes you'll see a little bit of valve float that takes place, and it can it can come into some piston to wall clearance, or piston to valve clearance issues. So we have specifications we set our heads up to ensure that doesn't happen. But keep in mind, the deeper you go with the valve recession, the more you're actually, or the less spring pressure that you're actually having on your seat pressure anyways, because you're moving everything. The geometry of this thing is moving away from the piston, and it's moving upwards, if you want to think of it in terms of that kind of geography there. So it's loosening up the spring. So guys that are cutting these things really, really deep but aren't doing anything to combat that can definitely lead to themselves some problems with valve floating and different things like that. So it's important. And I'm not going to get into that because it's not really something that is exclusive to the 6-liter as far as failures are concerned. But any cylinder head, it doesn't matter if it's a gas burner, if it's diesel, or whatever it might be, it's extremely important to pay close attention to the geometry of the valve train, because it does affect everything else. Something that you're going to note that we do differently, our workhorse engines all come standard. This O-ring that's around here, you can tell that the groove's been cut in it. But I've got another picture that might be a little bit better for you than that. And it is the O-ring cylinder heads that we provide. So these basically are providing a heat sink into the gasket, and it transfers, again, kind of going back to that whole combined gas law thing. But it does provide a heat sink into the gasket. I know personally, I've ran, we've got an excursion that I did some testing on with O-ring, and we were able to push as far as boost pressures are concerned, without any compromising of head gaskets, we were running at least 75 pounds of boost just on that excursion. And we're able to, I've tried it both ways. I've tried it a couple of different ways, and I've looked at different placements on that wire. But anyways, we were able to successfully run a consistent 75 pounds of boost, 80 pounds of boost on that truck. Now, it's a measurement of restriction, I understand. But running larger turbochargers is absolutely necessary to run O-ringing on the cylinder heads to make sure that we really don't have any. It does a couple of things. It does, like I said, the heat sink that it provides, but also it keeps the gasket from moving in high duress situations. So we've seen great success from the O-ring, and it's important. The placement of it's everything, because I've seen guys that did O-ring cylinder heads and they were the cause of the head gasket failure because of the placement being wrong. So that's extremely critical when you start doing this. It's not every guy out there that's doing things that are doing things the same. So that's something that comes standard, like I say, with our workhorse model, and that is that's an option that's available in other models as well. We've talked a little bit about the failures today. Now let me tell you a little bit about what we do different with the 6-liter. Obviously, the Model C engines that you see that we provide are always at the bare minimum going to fix what the OE problems were. It doesn't matter what the cost to us is to fix that problem. I don't want to send an engine out and it knowingly has a problem from the supplier. And we see this so many times in teardown. We know what's failing. We get to see it because it's a day-to-day thing for us. So we address that. We combat that with whatever parts or machining or processes that are necessary to ensure that you don't have those problems. The 6-liter, the things that we do, obviously ARP studs or some type of stud, that head stud to increase the clamp load of the cylinder heads. Some of the things that we do different is, like, for instance, on this particular cylinder head, you see the cracking that's going across from the glow plug to the injector. Now, quite frankly, I've not seen anything detrimental occur from that. A lot of people have a misunderstanding. There are some surface cracks. Now, here's the concern of surface crack. Is it going to go anywhere else? Is it going to stay where it's at? So that's always a concern there. That's the reason why we mag check. And if it does not meet our standards, then we do not use it. The seats are a parent metal seat that was induction hardened. What happens is they tend to, after so many heat cycles, they get brittle. They wind up cracking, and that crack expands beyond just the seat. It's pretty common. We've seen Cummins change from an integrated seat, like I'm talking about, to a press-in seat, which is what we've gone to. This reduces the cracking that we've seen in the seat areas, and it gives a little bit more longevity to the wear of those seats. It's just it's a much better solution to the problem. So our cylinder heads all come in with press-in seats from the daily driver, the workhorse, and obviously the Cass Watch. They're all press-in seats. The Model Cs are seats that are actually cut, and they're cut to the parent metal. So there is some value that's added by going to stepping up to to the daily driver. That comes with a 5-year, 100,000-mile warranty. Some of the other things there, you can see oil starvation that's occurring. Actually, that picture shouldn't have got in there, because I see this is actually a good point though. 6-liters typically don't have bottom end failure, and there's a reason for that. We don't see a lot of spun bearings unless a good buddy of mine works for. He was a bearing engineer, still is, for Mala, and he worked for NASCAR for Roush Chase for 27 years, I believe it was. And the only, well, I certainly would say the only, but one of the 6-liters that I've seen fail with bearings, funny enough, unfortunately for him, was his truck. And the reason for it was because the failure was actually the standpipe. On the top of the standpipe, there where my index finger is, there's a check valve. There's a ball, and that ball inside that is actually for I didn't even think about this, or I would have had a better picture until I started to discuss it. but that is the oil bypass. If the filter gets clogged, that valve will, it's a weaker spring. It'll overcome that valve, or that spring, I'm sorry, inside of that check ball, and it'll push past that. And that way, even though the filter's clogged up, now it's an oil bypass so that it can make sure that oil still gets to it. The issue with the 6-liter is this. The 6-liter is by far plagued with two things, the oil cooler design and we'll just group those together, the oil cooler / EGR cooler design. And the other thing is at any given time, and I want you, if you don't remember anything else about this, especially if you're a guy in the sales department, a girl in the sales department are working, this is important to tell the customer when they're installing. A 6-liter and a 6.4 are only one oil change away from complete detonation. I mean, it's literally one oil change away. That's the sad part about it. All it takes is one botched oil change where someone does not realize that oil bypass valve, or there's a check valve in the bottom here, and I don't know if you can see that or not, but it's down there towards the bottom, and it's actually missing on this one. But there's a check valve, and that check valve keeps the oil from draining out of the filter housing, so you don't have dry startups. If they come out, which is very common, because they're plastic, that's the only thing that's holding them in is plastic tanks. But if they come out, then it will wind up. It has the potential to take out your engine, as did, and unfortunately, my friend that I was telling you about had his oil changed at, we will say, a very reputable, we'll just say that, a very reputable shop that everyone has probably done business with if they own a Ford truck. But anyways, it can happen, and if you're not paying attention. So whether you're listening to this and you're a truck owner, or you're a shop, or you're a salesperson, or just whatever it might be, the one big takeaway, and we did a video called what it takes to, I think, how to kill your new diesel engine. And we go a little bit deeper into some of the things that can cause those failures. But that standpipe, someone should do an article based off of that alone, because that's caused more failures than Ford Motor Company would care to admit to. This is kind of a brief overview. I know it's only an hour long, and there's a lot of information in it. I could go a lot deeper, unfortunately, on these things. Just some of the spots that we hit on, some of the stuff on the 6.4 last week. Guys really, really bad about changing their transmissions out with 5R110s. We mentioned last week. If you have not watched that video, please check out the YouTube page, because we cover that in the 6.4 liter, that there's 220 grams difference between the flex plate on the 6.0 than there is the 6.4, because the rotational assembly is a lot larger on the 6.4 liter. And they're trying to take the 5R110. They'll just swap the converter. Instead of swapping the converter, let me change that. They'll swap the flex plate. So they'll take a 5R110 out of a 6.4 liter, and instead of changing the converter, what they'll wind up doing is they will pull the flex plate off, and they'll run a 6.4 liter flex plate. The difference is there's 8 bolts on the 6.4 liter flex plate, where there's 6 bolts on the 6 liter flex plate, but there's 220 grams difference. You'll have tremendous amount of imbalance, and eventually it'll wind up taking out the bearings on the engine. There's a lot of different ways to kill this thing, not nearly as many as there is on the 6.4 liter, but this should give you a pretty good overview of the things going on the 6 liter, and how they can be, they can be affected drastically by, like I said, keep in mind, just an oil change. So I appreciate everybody watching. Please check out the other videos. Right now we've got the 6.7, the 6.4. Next week we'll be discussing the 7.3 liter and trying to walk through some of the different changes, some of the different models. I'll add this too. It's important to note for the sales staff to find out what year model. There were some things that had changed, and I want to cover this real quick because I forgot. The 2003, 2004 was the same year model. There was very little changes, and let me pull this up for one quick second. There was very little changes on the engine itself between the two, but they had what they call redundancy bolts that they got rid of around the bed plate area. They got rid of around the rocker area. There were some changes in the rocker arms. 04.5, they made a big change because of the The location of the injection control pressure sensor was right underneath the turbocharger on the earlier year models. And that was not a great spot for it because it got really hot and they were really hard to replace. And every person that's ever worked on a 6-liter hates the engineer's guts that decided to put them there because unless you've got tiny olive oil style arms, you really have a heck of a time trying to get back there to replace that. So they moved it up to the passenger side of the front. With that came the change in the revision of the rocker boxes, but also the oil rail. The early 03, it was a long straight rail where they went to the wavy rail in the 04.5 to 07. So those were some of the changes. Obviously, the turbochargers and the vanes that were changed in that. The injectors, the pistons were also changed when they went to the 04.5. The combustion bowl was actually moved slightly, as well as the injector bodies. The internals, they were actually made out of a harder material because of some of the wear properties there, or some of the wear that they were seeing on the 6-liter injectors. Other than that, there are nuance changes with, on the front covers and things of that nature, but nothing drastic, nothing like what we see in the 6.7, where it's just or even the 7.3 for that matter. But that pretty much gives you a good overall view of this platform, why they did what they did. And I appreciate everybody watching. Look forward to seeing you next week when we discuss the 7.3, the holy grail of all Powerstroke engines. So that should be fun. You guys take care, and we will see you soon.